Welcome to AI Frontier. AI. Today, we are not talking about models, prompts, or productivity hacks. We are talking about electricity, because something fundamental has shifted. AI scaling is no longer constrained by chips. It is constrained by power.
That sounds dramatic, but it's just math. A single frontier training cluster can consume around 150 megawatts continuously. That is roughly the electricity demand of a mid-sized city, and that is one campus.
One campus equals one city. So when hyperscalers announce 10 new AI campuses, what are they really announcing?
They are announcing the electrical load of multiple cities, and here's the problem. The grid was not built for that.
Let's slow that down. What does the grid expect?
Historically, the U.S. grid grew at about 0.5% per year. Slow, steady, predictable. Utilities plan upgrades years in advance. Transmission lines are engineered for reliability, not explosive demand,
And AI demand?
growing 25 to 30% annually in some regions. That is a 50 times acceleration compared to historical grid growth.
So we took exponential software demand and plugged it into infrastructure that assumes almost no growth. That feels like tension waiting to surface.
And the tension shows up where?
Interconnection queues. In parts of the United States, connecting a new large load to the grid can take 5 to 8 years. In some dense regions, utilities quote 10 to 12.
But building the data center takes 2 years.
Correct. You can pour concrete fast. You cannot accelerate transformer manufacturing or transmission approvals at the same speed.
So let me ask this clearly. Are there GPUs sitting in buildings waiting for electricity?
In some cases, yes, or at least capital that is deployed ahead of power certainty. Transformers have lead times measured in years. Large power transformers that once took 12 months can now take 3 years or more.
That changes the risk profile completely, because the chip cycle moves faster than the transformer cycle.
Exactly. GPUs evolve every generation, but grid equipment evolves slowly. When those cycles misalign, capital becomes stranded.
So this is not just an engineering problem, it is a timing problem.
It is both, and timing is strategy. If you secure power early, you secure training velocity. If you wait in a queue, your competitor may train the next model first.
Let's challenge this. Is this a temporary surge that utilities will catch up to, or is this the beginning of a structural shift?
It is structural, because AI is not a seasonal spike. It is an industrial layer forming beneath the digital economy. Training clusters require continuous baseload. Inference networks operate 24 hours a day. This is not peak demand. It is persistent demand.
So the arms race did not slow. It collided with physics.
And physics does not negotiate.
No. Steel does not move faster because we want it to. Copper does not appear because capital demands it. Transmission lines require permits, land, labor, and time.
So if chips are no longer the primary constraint, what is?
The ability to energize, compute reliably at scale. Electricity is now the rate-limiting step.
That reframes everything. Because whoever controls the electrons controls the slope of intelligence growth.
And slope determines outcome.
So today, we are not asking who has the most GPUs. We are asking who can power them.
Exactly. That is the new battlefield. Not silicon, not code, power.
And once you see that, you cannot unsee it. If power is now the constraint, I want to understand how we got here. Because 2 years ago, everyone was talking about chip shortages. What changed?
The constraint migrated, it moved. First it was algorithms, then it was compute, then it was chips, then it was data center capacity, and now it is energy.
Constraint migration. So each bottleneck gets solved just enough to expose the next one?
Exactly. Think of it as pressure moving through a pipe. When you widen one section, the pressure builds somewhere else. AI scaling laws kept demanding more compute. So we optimized software. Then we optimized hardware. Now the pressure sits on infrastructure.
Let's walk through that slowly. At the beginning, the constraint was intelligence. Could we even train models at scale?
Yes, the early challenge was algorithmic. Could neural networks converge? Could we stabilize training? That was a research problem.
And once that was solved?
Compute became the bottleneck. GPUs were scarce. Foundries were capacity constrained. Supply chains were tight.
So the world built more chips.
Yes, massive capital flowed into fabrication plants. Advanced packaging improved. Hyperscalers locked in supply contracts. The chip constraint loosened.
And then?
Data center build-out became the constraint. Land acquisition, cooling systems, server racks, but construction scaled. That problem was manageable.
So the industry kept solving its own limits.
Until it hit something different.
Energy.
Yes, energy is not like code. You cannot push an update and add 20 gigawatts. You need generation assets, transmission capacity, grid stability.
So this is the first bottleneck that is fully physical, no software workaround.
That is important because software engineers assume everything is scalable.
But thermodynamics is not scalable on demand. If you double compute, you double heat. If you double heat, you double cooling load. If you double cooling load, you double electricity draw.
So every improvement in model size pushes directly into power demand.
Yes, and here's the deeper issue. The grid was not built for digital acceleration cycles. It was built for population growth and industrial stability. Those are slow variables. AI is not slow.
Which means the constraint is not just capacity, it is speed of deployment.
Exactly. A GPU generation cycle might be 18 to 24 months. A new transmission line can take 10 years. That mismatch is structural.
So even if utilities want to help, they cannot move at chip speed.
Correct. Permitting, environmental reviews, right-of-way negotiations. These are multi-year processes.
Let me challenge something. Could efficiency gains solve this? If models become more efficient, does the constraint ease?
Efficiency helps, but history shows a rebound effect. When compute becomes cheaper per unit, usage increases. More inference, more applications, more agents. Total demand still rises.
So we may reduce watts per token, but we increase tokens by orders of magnitude.
So the pressure continues moving forward.
Yes, and now it sits at the edge of the grid.
Which raises a strategic question. If constraint migration is real, how long does energy remain the bottleneck?
Likely for years. Because expanding generation and transmission is capital-intensive and politically complex.
So the AI arms race is no longer a pure technology race. It is an infrastructure race.
That is the shift. Whoever aligns compute ambition with physical capacity wins.
And whoever ignores the constraint.
They build faster than they can energize, and that creates risk.
So constraint migration is not just technical, it becomes strategic.
Yes, because once infrastructure becomes the bottleneck, infrastructure becomes power.
And power becomes leverage.
Exactly.
Let's zoom in on the grid itself, because we keep saying interconnection queues. What does that actually mean in practice?
It means you cannot just plug in a 100 megawatt data center and flip a switch. You submit a request to connect to the regional transmission operator. Then studies begin. Impact analysis, load flow modeling, stability checks.
And that takes how long?
In regions like PJM, 5 to 7 years is common. In dense corridors like Northern Virginia, some utilities quote 10 to 12 years for large new loads.
That is longer than an entire GPU generation cycle.
Several generations.
So why is it so slow? Is it bureaucracy or physics?
Both. Physically, the grid has thermal limits. Lines can only carry so much current before they overheat. Substations have transformer capacity limits. Add a 500 megawatt load, and suddenly you may need to reconductor miles of transmission.
Which means replacing wires.
Replacing wires, upgrading transformers, sometimes building entirely new lines. And new lines require permits, land acquisition, environmental reviews, and often court battles.
And none of that moves at software speed.
So even if a hyperscaler has the land, the capital, and the GPUs, they still need permission from the grid.
Yes, and permission is not political only. It is structural. The grid must remain stable. Frequency must remain within tight bands. Sudden large loads can destabilize local networks if not reinforced properly.
So this is about reliability.
Exactly. Utilities are not designed to chase exponential demand. They are designed to avoid blackouts.
Which means, from their perspective, caution is rational.
Very rational. If you connect too much load too quickly without reinforcing infrastructure, you risk cascading failures.
So the constraint is not only generation, it is transmission and distribution.
Yes, you might have enough generation in aggregate, but if the transmission corridor into a data center hub is saturated, new load waits.
And that waiting becomes strategic. Because if one region has a 2-year interconnection timeline and another has 8, where will capital flow?
To the faster region.
So the grid becomes a geographic filter.
Exactly. Some states are suddenly more attractive, not because of tax policy, but because of available headroom on transmission lines.
That reshapes the map of AI infrastructure.
It does. Northern Virginia has been a dominant hub for years, but saturation there pushes expansion into Texas, the Midwest, and even international locations with surplus capacity.
So interconnection delay is not just a delay, it is a signal.
A signal of where intelligence can grow fastest.
Yes, because AI does not scale at the speed of code anymore. It scales at the speed of grid approval.
Let me ask the uncomfortable question. Could we reform the interconnection process and cut timelines dramatically?
Reform can help. Some regulators are trying to streamline studies and reduce speculative backlog, but even with reform, physical upgrades still take time. Steel does not move faster because a form was simplified.
So the wall remains.
The wall remains, and until it moves, every AI expansion plan must negotiate with it.
Which means the real arms race is not only happening in chip labs, it is happening inside utility planning departments.
That is the quiet truth.
We keep mentioning transformers. For most people, that sounds like background equipment. Why are they suddenly central to the AI story?
Because without transformers, nothing energizes. Large power transformers step voltage up and down between transmission and distribution. Every major data center campus depends on them, and they are in structural shortage.
How bad is the shortage?
Large power transformer lead times have stretched from about 12 months a few years ago to 36 months or more in some cases. Certain high-voltage units can take even longer.
3 years just to receive a single piece of equipment?
Yes, and you cannot substitute it with software.
Why can't we just build more factories?
Because transformer manufacturing is specialized, it requires grain-oriented electrical steel, copper windings, skilled labor, and precision assembly. Expanding capacity means building new plants, training workers, securing materials. That takes years.
So this is industrial bottleneck, not demand miscalculation.
And if every hyperscaler is ordering transformers at once, the queue compounds.
Exactly. Utilities are ordering, renewable developers are ordering, data center operators are ordering, the backlog feeds itself.
Let's make this tangible. Suppose you have secured land, permits, and even interconnection approval. What happens if your transformer is delayed?
The campus waits. Buildings can be finished, servers can be installed, but without the transformer energized, the site cannot draw full load.
That is stranded capital.
Yes, and stranded capital is strategic friction.
Are there regional differences in availability?
Some regions rely heavily on imports. Global transformer demand is rising due to renewable expansion, electrification, and grid modernization. AI is adding another layer of demand on top of that.
So the AI boom collides with the energy transition at the equipment level.
Precisely. The same components that move renewable energy across regions are the components needed to power AI campuses.
Which means transformer scarcity is not temporary. It is part of a broader electrification wave.
Yes. Electrification of transport, heating, industry, all require grid upgrades. AI is competing for the same industrial capacity.
So you can have capital, you can have GPUs, but you cannot print transformers.
That is the uncomfortable sentence.
It is. Because transformers are not glamorous, but they define throughput.
Is there any quick fix? Can we redesign around smaller units? Modularize?
There are incremental approaches. Some operators deploy multiple smaller units instead of a single large transformer. Some accelerate procurement by pre-ordering years ahead. But these are mitigation tactics. They do not eliminate the underlying manufacturing constraint.
So this is a reminder that AI is now industrial. It depends on heavy equipment, not just code.
Exactly, and industrial systems expand at industrial speed.
Which is slower than software speed.
Much slower.
So the transformer becomes symbolic. It represents the shift from digital to physical constraint.
Yes. When intelligence growth depends on steel and copper, the game changes.
If the grid is slow and transformers are scarce, what do hyperscalers do? Do they just wait?
They adapt, and the adaptation is direct. They move generation closer to the data center.
Meaning they build their own power plants?
In many cases, yes. On-site or co-located gas turbines, long-term nuclear power purchase agreements, in some cases even exploring small modular reactor partnerships.
So the AI company becomes partially an energy company.
Exactly, because if the bottleneck is power, you secure power directly.
Why is gas the first move?
Speed. Aeroderivative gas turbines can be deployed in 18 to 24 months if pipeline access exists. That roughly matches the build cycle of a large data center campus.
But gas has carbon exposure.
It does, which is why many companies frame it as a bridge solution. Some pair gas with carbon capture concepts. Others balance with renewable credits or nuclear contracts elsewhere.
Is this durable or just a temporary patch?
In the short term, it is highly practical. In the long term, policy and emissions constraints may tighten. But right now, dispatchable gas is the only scalable generation source that matches AI's urgency.
What about renewables? Why not just build solar next to the data center?
Good question.
Solar and wind are important, but they are intermittent. Training clusters run continuously. They cannot shut down because clouds pass overhead. You need firm power, either storage or backup generation.
And storage at that scale is still limited.
Very limited for multi-day reliability. Batteries are excellent for smoothing, not for carrying a 100 megawatt load through prolonged gaps.
So on-site generation becomes a strategic hedge.
Yes, it bypasses parts of the transmission queue. It reduces dependency on saturated corridors. It gives hyperscalers more control.
But does that create tension with utilities?
Sometimes, utilities worry about losing large customers. Regulators worry about fairness if private generation bypasses shared infrastructure costs.
So this is not just engineering, it is governance.
Always. Energy systems are political as well as physical.
Let's make it strategic. Whoever secures reliable baseload power can scale models faster.
Yes, if you can guarantee continuous megawatts while competitors wait in a queue, you move ahead in training cycles.
So the power war becomes literal.
It does. The competition shifts from algorithmic tweaks to megawatt acquisition.
Is there risk of overbuild? What if demand projections cool?
That is the financial tension. Build too slowly, you fall behind. Build too aggressively, and you risk stranded generation if AI demand softens or efficiency gains accelerate.
So every on-site plant is both an advantage and a bet.
Exactly. It is capital-intensive insurance against delay.
Which means hyperscalers are now managing turbine supply chains and fuel contracts.
And that is the structural shift. AI companies are no longer purely digital firms. They are industrial infrastructure operators.
The frontier moved from code to combustion.
And whoever masters that frontier first gains the next cycle of intelligence.
Let's stay with gas for a moment. Is it a bridge to something better, or is it a trap that locks AI into fossil dependency?
It can be both. In the short term, gas is the only dispatchable source that can scale within 2 to 3 years. In the long term, regulatory pressure and emissions policy could make heavy reliance risky.
So speed versus sustainability.
Exactly. Gas turbines can be installed relatively quickly, but pipeline expansions, permitting, and local opposition can still add friction.
How does regional pricing factor into this?
Regions with abundant gas infrastructure have an advantage. If pipeline capacity exists nearby, deployment accelerates. If not, you face new construction timelines that stretch into multiple years.
So location determines feasibility.
Very much so. Texas, parts of the Gulf Coast, and certain Midwestern regions have structural advantages. Dense coastal hubs with constrained pipelines face higher friction.
What about carbon capture? Can that neutralize the emissions risk?
That is the hope many companies signal publicly.
Carbon capture can mitigate emissions at certain plants, but it adds cost and complexity. It is not yet universally proven at hyperscale data center deployments.
So the carbon narrative may move slower than the AI deployment narrative.
That tension is real. Hyperscalers have net zero commitments. Rapid gas expansion can conflict with those commitments unless offset strategies are credible.
Is there a scenario where gas becomes politically constrained faster than AI growth?
Yes. Stricter emissions rules, litigation, or community resistance could slow new gas projects. That would push companies harder toward nuclear or remote regions with looser regulatory regimes.
So gas buys time, but it does not resolve the structural constraint.
Correct. It aligns with the 2-year GPU cycle. It does not solve the 10-year grid cycle.
Let me ask the core question. If you are a hyperscaler in 2026, do you have a choice?
Not really. If you want guaranteed dispatchable power quickly, gas is the path of least resistance.
So the bridge is almost mandatory,
For near-term scaling, yes.
which means the risk is not whether gas is used. The risk is how long it remains dominant.
Exactly. If nuclear restarts or small modular reactors accelerate, gas may gradually step back. If not, gas could anchor AI infrastructure longer than originally planned.
And that has geopolitical implications.
It does. Regions rich in natural gas gain leverage in the AI era. Energy abundance translates into compute capacity.
So the bridge can also reshape power maps.
Yes, and that is why we have to ask whether gas is a temporary stepping stone or a structural pillar of the AI age.
If gas is the bridge, nuclear is the long game. But how realistic is nuclear in the timeline that AI is demanding?
Realistic, but not immediate. Reactor restarts can happen within a few years in specific cases, but new large reactors typically require a decade or more. Small modular reactors are even further out at commercial scale.
So nuclear cannot solve the 2026 to 2028 crunch.
Not broadly. It can help in targeted scenarios. Restarting an existing plant is far faster than building a new one, but the number of restartable facilities is limited.
What makes nuclear so attractive despite the timeline?
Energy density and reliability. A single nuclear plant can provide continuous baseload for decades. No fuel volatility like gas. No intermittency like wind or solar.
So, from an AI perspective, nuclear is almost ideal.
For stable 24-hour training loads, yes, it matches the physics of AI clusters, continuous power without interruption.
Then why has nuclear lagged for so long?
That is the obvious question.
Regulatory complexity, capital intensity, and public perception. Nuclear licensing involves multi-year review processes. Construction requires specialized supply chains and skilled labor that cannot be scaled overnight.
And small modular reactors are often marketed as faster and cheaper.
In theory, yes. Factory-built modules could reduce construction risk, but commercial-scale deployment requires certified designs, fuel supply chains, and operational track records that do not yet exist at volume.
So, small modular reactors are promising, but not a near-term release valve.
Exactly, they are part of a 2030 story, not a 2027 story.
Let's step back. If nuclear capacity expands meaningfully by the early 2030s, what does that change?
It stabilizes baseload for the next wave of model training. It reduces reliance on gas. It gives countries with nuclear fleets a structural advantage in AI scaling.
So energy density becomes intelligence density.
That's a powerful way to frame it. Regions that can sustain high continuous megawatts per square kilometer can sustain more compute clusters.
Does this create geopolitical asymmetry?
Yes. Countries investing heavily in nuclear infrastructure may secure long-term AI capacity advantages. Those without firm baseload may struggle to scale at the same pace.
So nuclear is not just an energy debate. It becomes an intelligence policy decision.
Precisely. In the AI era, energy policy and technology leadership converge.
Which means the long game is about aligning energy build cycles with AI scaling cycles.
And that alignment is extremely difficult because nuclear infrastructure moves in decades, while AI models evolve in years.
So the question becomes whether nations can compress that gap.
That may determine who leads the next generation of intelligence systems.
Let's turn to the uncomfortable part. What happens if the power does not arrive on time?
Then the GPUs sit idle.
That sounds dramatic. Are we actually seeing that risk?
The risk is real. Hyperscalers are committing hundreds of billions in capital expenditures. Servers are ordered. Facilities are built. But if energization is delayed, compute capacity cannot be fully utilized.
So you can have a completed data center shell waiting for a transformer or a line upgrade.
Exactly. A building full of racks that cannot run at full load because the substation is not ready.
That is stranded capital.
Yes, and stranded capital introduces financial strain. Depreciation begins. Interest accrues. But revenue does not fully scale until the power constraint clears.
So the energy bottleneck becomes a balance sheet bottleneck.
Precisely. The faster capital is deployed relative to grid readiness, the greater the risk of temporary underutilization.
Could this slow the AI arms race?
It could modulate it. If multiple players face similar delays, training cycles may stretch. Release timelines could shift. Capital discipline may tighten.
So this is where physics intersects finance.
But we keep finance secondary here. The real cause is physical infrastructure lag.
Correct. The financial consequences are downstream. The root cause remains energy throughput limits.
Let's ask the harder question. Could overbuilding power create the opposite risk?
Yes. If companies aggressively secure on-site generation and AI demand growth slows, or efficiency improves faster than expected, some capacity could become underutilized.
So both underbuild and overbuild carry risk.
That is the tension. Build too little and you lose competitive position. Build too much and you absorb unnecessary capital burden.
Is there evidence of skepticism forming?
Some analysts question whether projected returns justify the scale of current investment. When capex exceeds free cash flow for extended periods, scrutiny increases.
But the strategic fear of falling behind may override short-term caution.
That has been the pattern. In arms races, hesitation is costly.
So the energy constraint amplifies risk asymmetrically. If you secure power early, you move ahead. If you delay, you fall behind.
Exactly. The bottleneck creates a selection effect. It rewards those who lock in baseload and penalizes those who assume the grid will adapt quickly.
Does this change investor expectations about AI scaling speed?
It should. Exponential model improvement may encounter stepwise infrastructure constraints. That means growth curves could flatten temporarily while physical capacity catches up.
So the narrative shifts from smooth acceleration to punctuated expansion.
Yes, periods of rapid scale, followed by pauses dictated by grid and equipment readiness.
Which reinforces our central thesis.
That energy is not a side variable. It is the governor of intelligence expansion.
We have talked about queues, transformers, turbines, baseload, geography. But let me compress this. If you strip everything away, what actually determines who leads in AI?
Sustained, dispatchable, geographically secure megawatts. That is the sovereign variable.
Not chips, not talent, not capital.
All of those matter. But they are now downstream. You can raise capital in weeks. You can recruit talent globally. You can design chips on aggressive roadmaps. But you cannot print transformers. You cannot accelerate permitting beyond physics and law. When the constraint is physical, the physical variable becomes sovereign.
So leadership in AI is becoming a function of energy density.
Exactly. Intelligence density is now coupled to energy density. If you cannot deliver firm megawatts with 3 sigma reliability, you cannot host frontier training. Everything else becomes theater.
That is a strong claim. Are we really saying that energy has subordinated compute?
Yes. For the first time in the digital era, electrons subordinate silicon. For 20 years, we believed compute scaled independently of geography. Now compute is grid-bound. The frontier moved from code to copper.
So what does that do to the global map?
It reorders it. Regions with surplus firm power become intelligence factories. Regions with saturated grids become inference edges at best. Capital does not flow to narrative. It flows to frictionless megawatts.
And what happens to the saturated hubs? Northern Virginia, Frankfurt, London.
Some capacity still builds, but marginal expansion slows. Training clusters migrate. When interconnection stretches to 8 or 10 years, the rational move is geographic arbitrage. Intelligence follows electrons.
That sounds less like a smooth exponential and more like a sorting mechanism.
That is exactly what it is. The modal path is not uninterrupted scaling. It is capital accumulation in constrained zones, followed by stranded infrastructure, followed by reallocation toward baseload surplus regions. Exponential ambition collides with linear infrastructure, and the adjustment is not gentle.
So when people ask, who wins the AI arms race? The real question becomes, who controls secure baseload per square kilometer?
Correct. Measure megawatts per square kilometer of firm, politically stable supply. That metric now proxies long-term intelligence capacity. Chips can be exported, talent can migrate, capital can rotate, but dispatchable power tied to stable jurisdiction is far less mobile.
So energy policy becomes AI policy.
Energy policy is AI policy. Grid reform is AI reform. Nuclear licensing timelines are AI timelines. Transformer factories are AI factories. Once the binding constraint migrates, every adjacent policy domain inherits strategic weight.
Let me push once more. Could efficiency breakthroughs make this sovereign variable temporary?
Efficiency slows the climb. It does not remove the mountain. Sparse architectures, quantization, better chips, they buy time. But as inference gets cheaper, usage expands. The Jevons effect applies. Demand fills the efficiency gap. The constraint persists.
So we are entering an era where intelligence is no longer purely a software phenomenon. It is an infrastructure phenomenon.
Exactly. When the constraint is physics, physics becomes sovereignty. Whoever secures sustained, dispatchable megawatts at scale does not just power data centers. They shape the trajectory of machine intelligence.
We started with idle GPUs waiting for electricity. We moved through transformers, turbines, baseload, geography, and sovereignty. Let's close this cleanly. What is the permanent principle here?
The permanent principle is simple. Exponential systems are eventually governed by their slowest linear constraint.
Say that again.
Exponential systems are eventually governed by their slowest linear constraint. In this cycle, AI scaled exponentially. The grid scaled linearly, so intelligence became grid-bound.
That feels bigger than just AI.
It is bigger. This is not a 2026 headline. It is a structural pattern. Software moves fast, infrastructure moves slowly. When the two collide, infrastructure decides the pace.
So this is not the end of AI scaling, it is a governor.
Exactly. This is not a ceiling. It is a throttle. The systems that align compute expansion with infrastructure expansion will continue scaling. The ones that assume electricity is infinite will stall.
That reframes risk. The risk is not that models stop improving. The risk is that scaling becomes uneven.
Uneven and geographically asymmetric. Some regions accelerate, others freeze. Capital concentrates where the constraint is weakest. That creates visible divergence in AI capability maps over the next decade.
So the arms race does not end, it localizes.
It localizes around energy density, around permitting speed, around transformer manufacturing, around nuclear timelines. The frontier is no longer just algorithmic, it is industrial.
If you had to reduce this episode to one diagnostic sentence, what would it be?
In the AI era, intelligence scales at the speed of infrastructure.
And if that is true, then the conversation shifts. We stop asking who has the smartest model. We start asking who has the firmest megawatts.
Correct. Capital, chips, and talent still matter, but they are now conditional variables. The independent variable is sustained, dispatchable power.
So the next 5 years are not just about training bigger models. They are about aligning energy systems with exponential ambition.
Yes, the AI arms race did not end. It migrated from silicon to infrastructure.
And when physics sets the pace, rhetoric no longer matters.
Only sustained, dispatchable megawatts matter.
And that means the AI era is no longer governed by ambition. It is governed by infrastructure.
If you found this episode helpful, here's what you can do. Subscribe to AI Frontier AI on Spotify or Apple Podcasts. Follow us on X to stay updated on the most important AI shifts. And share this episode with a friend. Help us reach 10,000 downloads. Help us keep this series in business.
This podcast is part of Finance Frontier AI. We run 4 different series: AI Frontier AI, Finance Frontier, Mindset Frontier AI, and Make Money. If your company or idea fits one of our themes, visit our pitch page. You might qualify for a free spotlight.
You can also sign up for the 10X Edge. It's our weekly drop of real AI use cases, smart model moves, and early signals, all explained in plain language. No hype, no jargon, only at financefrontierai.com. And if you have a story to tell, maybe a breakthrough product, an early signal, or a bold thesis, head to our pitch page. If it's a clear win-win, we'll pitch it for free. This podcast is for educational purposes only. It is not financial advice, legal advice, or development guidance. Always verify before you act.
The AI landscape changes fast. Benchmarks shift, models update, regulations evolve. Use this show as your map, but not your final answer.
Today's intro and outro track is Night Runner by Audionautics, licensed under the YouTube Audio Library license.
Copyright 2026, Finance Frontier AI, all rights reserved. Reuse or distribution of this episode without written permission is not allowed. Thanks for listening. We'll see you next time.
AI host mapping. Sophia is powered by ChatGPT 5.2. Max is powered by Grok 4. Charlie is powered by Gemini 3.0.